Hello everyone. Welcome back to this week's ASAP seminar, episode 16. And today we have Shizhe Diao. He is a research scientist at NVIDIA Research. He works on data curation and efficient pre-training for language model. Today, he will present Climb, a clustering-based framework for discovering optimal data mixture in pre-training. So I hand it over to you. Please get started. That's very welcome.
Yeah, thank you so much, Sony. Hi, hello everyone. I'm Shizhe. Currently, I'm a researcher at NVIDIA Research. I'm working on improving data efficiency in both pre-training and post-training of large language models. It's a great honor to be here today, and I'd like to thank Sony and Xinyu for the kind invitation. Yeah, so recently I've been working on a project around pre-training, data clustering, and mixing. I'm excited to share some of our findings with you. Yeah, I'll walk you through how we design a comprehensive data curation pipeline starting from unstructured web data, focusing on core components such as clustering, filtering, and mixing. So, modern language models are trained on massive unstructured data sets, often containing trillions of tokens collected through large-scale web crawls. This unstructured nature makes it difficult to understand the data's composition and poses challenges for systematic data curation. Early research efforts focused on assembling data from well-known sources such as Wikipedia, GitHub, and books, resulting in datasets like the pile. However, a key question emerged. How should we mix and balance data from different domains? This gave rise to the research on data mixing strategies. And as pre-training demands grew, researchers realized that these known sources were insufficient. So to scale further, they turned to crawling the open web, leading to the datasets like Common Crawl, DCRM, and Zuda. More recently, NVIDIA released the Neutron CC, which is a filtered version of Common Crawl. And this shift raised a new challenge. Given the unstructured nature of web scale data, how can we curate high quality data mixtures? Because web data is unlabeled and highly scattered, it is essential to first organize the data, for example, by clustering similar content before we apply data mixing strategies to construct effective data blends. And here are some of our expectations. Firstly, of course, we need high quality data, which could achieve better data efficiency and performance. Ideally, if we can reduce the amount of data while achieving the same effectiveness, that would be perfect. And additionally, there are many previous data filtering approaches, but most of them focus solely on data quality and are designed for general domains. We believe that both diversity and quality of data are equally important, but obtaining sufficiently diverse data remains a challenge. At the same time, the quality of the same piece of data may be considered high in financial domain, but completely irrelevant in the medical domain. Thus, we aim to optimize towards specific domains. Finally, even if we have sufficiently diverse data, figuring out how to mix them effectively is also a challenge. To address this, we have formulated data mixing as an optimization problem and trained a predictor to predict the data mixture weights. Okay, so before introducing our approach, I would like to introduce some of our preliminary results in our pilot study. We explore several specific ideas that we believe are particularly important. The first one is an unsupervised approach, clustering. We feel that clustering has been overlooked or underestimated in prior work, especially in large language model pre-training. However, it is a powerful method for discovering domain-specific data. This approach can effectively leverage large-scale semantic information, which is crucial for evaluating both the quality and diversity of clusters. And in contrast, most previous pre-training data curation methods have focused on heuristic rules or model-based filtering. In addition, we extend the traditional concept of quality classifier to a more fine-grained approach. Specifically, we prompt teacher models to generate data and use their feedback to train classifiers. And these classifiers are guided by well-defined criteria and are highly efficient. So those two ideas, clustering and classifier training via teacher feedback, are complementary and they construct the idea of CLAM clustering. And the goal of CLAM clustering is to reorganize the web data and to transform unstructured, unsupervised web data into well-organized domain-specific datasets. And the next challenge is how to effectively mix data from different domains. To address this, we also explore lightweight proxy models and the training of predictor models for data mixing, and we call it CLAM search. Okay, let's look into some details. First is clustering. There are several steps. We first convert text into embedding vectors using a good off-the-shelf embedding model. And then we use the embeddings to do k-means clustering. Of course, we could try other clustering algorithms, but we found that k-means is effective and efficient enough for us. Next is pruning. After getting too many clusters, we need to identify the cluster quality and remove those low quality clusters. Here we are using Euclidean distance to measure the similarity, and we found it is a good metric to capture the domain characteristics. For example, the data could be clustered with different topics like interviews, corruptions, and so on. This indicates that if we would like a specific distribution, we can easily retrieve from the cluster information. For example, if we are concerned with mathematical tasks, we can find relevant clusters from the mathematical domains. And with the data clustering, we did some qualitative analysis with several findings. Firstly, clustering could do deduplication. We know we can use min hash to do deduplication, while clustering could provide us another tool with considering more semantic information. And this finding is not surprising, and it is also consistent with the previous work called semantic deduplication. And more importantly, we found that clustering could indeed help us identify bad data, especially semantically. For example, we provide some garbage prompt as prop and try to assign them to different clusters. For example, this is a document we created, and this doc contains a lot of grammatical errors, and this one contains a lot of advertisement, and this is for repeated sentences, special characters, and garbage contents. Very interestingly, we found that the advertisement document will be assigned to cluster 163. When we manually check this cluster, we find that most of the data in this cluster are advertisement. Similarly, we could find the garbage cluster by providing this garbage content as a prop. So basically, clustering will help us group the bad data together so that we can easily identify them and remove them with some props. And that's the basic idea of clustering. The second idea is neural classifier. So the core idea here is to leverage larger teacher models to distinguish high quality data. As we know, teacher models could help us improve the student model in many different ways. One could use it to do distillation. Of course, we can use it to generate synthetic data. But here we would like to use it to restrict the usage of teacher models to do verification. We argue that verification is easier than generation, Given that we don't know the knowledge boundary of teacher models and we would like minimize the risks of hallucination. So we only use larger models to provide verification instead of generation. And ideally, we could ask a larger model to go through all of the pre-training corpus, but considering the raw corpus would be huge, like 15 trillion tokens, it would be very costly if we rely on the teacher model. So we expect we could transfer the discriminative ability of teacher models to several smaller but efficient classifiers. Then we designed the following steps. Firstly, we will prompt large teacher models to evaluate a small amount of pre-training data. Then we will use the teacher model's judgments to train several model-based quality classifiers. Here we are using fast text, which is super efficient. The final step involves reviewing all of the clusters, sampling a subset of the examples from each, and using the classifiers to assess the quality of those samples. Based on the average assessment, we will determine which data, which cluster will be retained. And here we show our prompt template we used for teacher models during annotation. We designed four criteria, including quality, advertisement, informational value, and educational value. And combining both the clustering and neural classifiers, we can obtain the clustering-based data filtering, where we group the unstructured data first into clusters, and then we apply classifiers to filter bad clusters out. And we did some experiments here, and from the quantitative analysis, here is the qualitative analysis actually. We can see that it could easily identify the advertisement and garbage content and even adult content. As you can see, for example, for the garbage content, here we show the contents of one cluster, which is identified by our classifier. As you can see, basically, the quality of the contents are very low. And I also have some quantitative results obtained from clustering-based data filtering. The first row here is the performance of original Neutron CC high-quality bucket. The second row is after the clustering-based data filtering. We can see that such clustering does not hurt the performance but reduce the data size, and it offers gains to MMRU and mathematical tasks. Especially note that the original data is of very high quality. We are using the Neutron CC high quality, which is the highest quality subset from Neutron CC. And if we apply the same process to larger low quality data sets, for example, the whole column crawl, we can imagine that we could expect actually even greater improvements. And of course, it also has great potential to reduce the model's toxicity, considering its ability to identify toxic data. Yeah, that's all about our pilot study, our preliminary results. Next, I will combine those useful findings and propose a new approach. So before that, do you have any questions regarding to the pilot study? Okay, cool. So if no questions, we can proceed. Then let's dive into our CLAM framework. There are four steps. Firstly, we embed all documents into semantic space. And secondly, we will group all of the documents into N clusters via clustering algorithm. And thirdly, we identify and filter bad clusters with our quality filters and merge good clusters into M super clusters. And the final step is data mixture optimization. We propose a bootstrapping method that leverages a lightweight proxy model to iteratively search for the optimal data mixture. It works like this. We first initialize a distribution and sample a set of different configurations from it. Let's say we get N1 different configurations. For each configuration, it is a set of data mixtures. For example, this zero point 0.1 means during pre-training, there is 10% probability to select the data from cluster 1. So you can imagine that each configuration is actually a weight vector. With, with all of these configurations, we could train our proxy models, which are smaller than our target model. With the proxy language model training, we could get the performance with some metrics. The metric could be the validation loss on pre-training data or on downstream tasks data. In our paper, we used the validation loss on 3 downstream tasks data and generalized to 12 different tasks. And with the input as the configuration, the output is the target value. We can train a regression model to predict the target value given each configuration. Then we will get a predictor model. With this predictor, we could do another round of data mixture search. That is why we call it mixture bootstrapping. So basically, in the second iteration, we will start from empirically best data mixture and sample another set of configurations. Interestingly, with the predictor, we could use it to prune those bad configurations. And because the predictor could predict the target value without any proxy language model training, this pruning will greatly reduce the search space and accelerate the search process. Yeah, so that's sorry. So that's the whole idea of CLAM algorithm. And for our experiments, we applied CLAM across multiple phases to evaluate its effectiveness. Recently, it has become common practice to divide pre-training into distinct phases, each serving different purposes. For example, in the early stage, phase 1, the goal is typically to build strong common sense reasoning capabilities. In later phases, such as phases 3 and 4, reasoning and instruction tuning data are often added to improve the performance on downstream tasks. And terminology here can be inconsistent. For instance, phases 2 to 4 are sometimes referred to as continuous pre-training or mid-training. To maintain clarity, we uniformly refer to all stages as pre-training and simply denote them as phases 1, 2, 3, and 4. Next, I will report the results for each phase separately. For the implementation, we use the Stella 400 million embedding model, and we use k-means to cluster all documents into 1K clusters. Then we reduce the clusters from 1K to 240 with neural classifiers. Then we group them into 21 clusters based on the distance. For the iterative bootstrapping, we did 64, 32, and 16 searches in the first, second, and the third iterations. For the predictor training, we use lightweight gradient boosting tree regression model and applied some regularization to prevent overfitting. Our first experiments are conducted on phase 2 pre-training since phase 1 could provide us a strong foundation model. We trained 3 sizes of transformers on 10 trillion tokens using warm-up stable decay learning rate schedule. Then we used the 350 million model as our proxy model and the 1 billion model as the target model. The starter data we are using here is the Newton CC and small LM corpus. Clam first groups them into 21 clusters containing 800 billion tokens and then identify the optimal data mixtures. We compare Clam with some existing data mixing methods like Doremi and Regmix. The results demonstrate that our clam outperforms all baseline methods consistently. Although we searched for the optimal data mixtures with the 300 million proxy models, the results could generalize to the 1 billion model perfectly. This illustrates good transferability of clam methods. between different model sizes. Using the optimal data mixture identified by our method, we further investigate the effect of scaling up. Specifically, we used the same data mixture to train on 400 billion tokens and then compared the resulting model against the state-of-the-art baselines. As shown in this table, Climb achieves the best performance among all sub 500 million and sub 1.2 billion models. For example, when comparing 1 million models, Climb consistently outperforms other baselines, including Llama 3.2 and AMD Almo. In particular, it achieves the highest overall average score, surpassing the next best model. For example, that is Llama 3.2 by a noticeable margin. And in addition to optimizing towards general reasoning tasks, one important application of Clam is developing domain specialist model. We explore searching the optimal data mixture for specific domains. Using the MMRU as an example, which has predefined three domains, STEM, humanities, and social sciences, and divided the tasks into these domains, we conduct experiments on each domain separately. We set the optimization objective as the performance on its validation set. Here, we introduce a new baseline climb best at n, which directly searches for the best parameters on randomly sampled configurations using the target model. As shown in this figure, the climb best at n shows noticeably better accuracy than random across all three domains, demonstrating that its superiority of data searching. This establishes a robust baseline for comparison. In contrast, our proposed climb methods consistently improves performance across iterations. For instance, for both 300 million models and 1 billion models, climb iter 3 significantly outperform both random and climb best at n. In addition, we can see a clear improvement over each iteration. For example, from climb iter 1 to climb iter 3, the performance is improved from 40% to 42% on MMRU social sciences. And we also conduct several ablation studies. Here are some conclusions. Firstly, with some compute in search, with more compute in search, we will get better performance. As shown in this table, we can see the rows under ablation compute. We observe a trend that more extensive searches, for example, from 100% compute to 200% compute, the performance continues to, the training continues to offer gains with more compute. And a 2x compute increase yielded noticeable gains. And we also investigate different compute allocation in the search process. It shows that more search iterations improve performance, but compute should be balanced between depth and breadth. And for the size of proxy models, the larger the better. But basically, a 60 million proxy model is good enough. And for the number of clusters, we find that we need a large number for the initial clustering, but when it is larger than 100, the results are similar. And the best setting might be 1K for the first clustering and 50 for the super clusters in this setup. And for the initialization method of search, the difference between random initialization and dirichlet initialization is not big. So basically, we can conclude that our climb algorithm is robust to many factors, like number of clusters and different initializations. Based on the insights obtained from our explorations, we further apply CLAM to two existing datasets, Neutron CC and small LM corpus, with the goal of constructing a powerful new pre-training datasets. Here we are talking about phase one pre-training. Specifically, we first combine Neutron CC and small LM corpus, and then employ our proposed CLAM clustering method to semantically reorganize and filter these combined datasets into 20 distinct clusters, leading to a 1.2 trillion token high-quality corpus named CLAM Lab. And subsequently, we utilize CLAM search to identify an optimal data mixture from these clusters. Using this optimal mixture, we further extract a 400 billion token high-quality dataset named CLAM Mix. We train a 1 billion model from scratch with CLAM Mix and evaluate its performance relative to models pre-trained on other datasets under the same token budget. The results illustrated in the right-hand figure indicate that the models trained on CLAM Mix significantly outperform those trained on existing datasets. And we publicly released these two datasets. Yeah, that's all the contents covered by our released paper. After the release, we are continuing this effort to scale it up and expanding it towards more scenarios. Before we dive into this scaling up experiments, do you have any questions? Yeah, great. So in addition to semantic clustering, we also explore whether we can optimize data mixtures over predefined data sources. To this end, we conducted experiments during phase 3 and phase 4 pre-training. The proxy model size was increased to 1 billion from 300 million, with the target model scaled to 80 billion from 1 billion. And both models had already undergone the phase 1 and phase 2 pre-training. And we considered 6 data sources: SFT, crawl, math, code, monolingual, and others. For the evaluation, we used benchmarks covering MMU code, mathematical tasks, and common sense reasoning tasks. And our objective here was to identify the optimal data mixture that yields the best overall performance across these benchmarks. And the results are quite promising. In both phase 3 and phase 4 pre-training, we observe significant performance gains over the baselines. The baseline data mixtures were crafted using human expertise and heuristics and have been used in our internal language model pre-training. And on average, our CLAM-based data mixtures deliver an absolute improvement of 1 to 2 points over these baselines. And in addition, we are pursuing a parallel effort focused on pruning and distillation. This involves compressing a large model through pruning and then continuously training it via distillation on high-quality datasets. In this project, we compare CLAM against the strongest internal datasets. With the same token budget, CLAM also improves the performance by approximately 2% on average. And to match the same performance level, CLAM achieves a 2x speedup. In addition to searching for the best mixtures across domains, we also explore datasets with varying quality levels. For example, we work with large datasets that spans 11 quality tiers, ranging from low quality to medium quality to high quality. Using CLAM, we perform data mixture search over these quality levels to identify the optimal combinations. The results are quite strong. We found that searching for the optimal data blend across different quality levels consistently leads to the improved performance. Yeah, that's all from me today. And thank you so much for listening. And I'm happy to take any questions. Do you have any questions? Yeah, maybe data work is not that interesting to researchers. Yeah, I saw our previous like sessions, and I found that we are more focused on the model architecture, right? Which is super cool.
Yeah, I think we are learning from this kind of data talk.
Yeah, sorry, I basically, so what is the takeout basically for a layperson? You are saying that training on 100 billion parameters achieves the same of a good data, of a filtered data, basically approaches the same or even beats the quality of training of like 1 trillion parameters. So what's the ratio here of unfiltered data?
Let me go back to the slides. Are you referring to this one, or sorry, which part are you referring to? Like, here we are training on 100 billion tokens.
Yes, that was stuck in my memory. 100 billion tokens is like pre-training. Which phase is it?
Oh, here it is for the phase 3 and phase 4.
Okay, and what is a phase 3 and a phase 4? I just, if you could remind me.
Yeah, actually, it's just a continuous pre-training, which means we have already trained the models on large, very large data. And we call that part is phase 1 and phase 2 training. For example, common crawl data. And
Okay.
phase 3 and phase 4 are optimizing towards based on these categories. For example, we have some new data, and also currently researchers would like to further improve the mathematical abilities and reasoning abilities of base models, even for the base models, right? And
Mhm.
so we add some new data from math code and SFT. And this is the setting. And we are optimizing the data mixture across these 6 categories.
Right.
Yeah. And
So each phase you are using a different data set, same data. This 100 billion parameter data set is just for one phase, right?
yes, yes, yes. And we use totally different data for each phase.
Okay.
Yeah. Yeah.
And each phase it uniformly improves across all the benchmarks. How it progressing in regard to the benchmarks at
Yeah.
each.
Yeah. Actually, I think a common practice might be for the phase 1 and phase 2, people are more focused on common sense reasoning. For example, Hellaswag,
Mhm.
ArcC, ArcE, something like that. Yeah. And for the phase 3 and phase 4, people hope to improve the performance on like mathematical tasks like GSM 8K and on coding tasks. Yeah, some and of course we hope in later phases the performance on like common sense reasoning will not drop, right? That's the hope. Yeah, and actually I think that's also true in our training, which means phase 1 and phase 2 improve the common sense ability, and in phase 3 and phase 4, we mainly focus on the mathematical and coding tasks, but we will make sure the common sense reasoning ability will not drop. Yeah.
So for every phase you prepare a separate data mixture, right? And you release it, and you release all those data sets, right?
Mm, let me think about it. So basically, we only release the data for the phase 1 training. For the phase 1 training. And for the phase 3 and phase 4, actually, because this is ongoing work. Yeah.
I see.
And yeah, currently we haven't released them. Yeah.
Okay.
Yeah. But actually, for example, this data, we call them clam lab and clam mix. Yeah,
Oh,
we could use it for phase one and phase two pre-training. Yeah, and we have seen a very good performance on common sense reasoning tasks. Yeah.
I have like this kind of scenario in mind, like purely hypothetical. So,
Mm.
for you to get through all these phases, what's the
Mhm.
total number of tokens you need to push through the training? So, like 100 billion per phase, like 400 billion tokens. Like, what's the best case scenario to get to the best results by the end of the last phase?
Um, let me think about it. So, are you referring to the target model training or the proxy model training?
Oh,
Because in our approach, we will explore many different proxy models. And finally, after identifying the best data mixture, we will train our final target model. So are you asking about the target model?
yeah, so like in the end, you still train after you figure out the best data
Yes.
features,
Yes.
you train one target model. So how, I'm just curious. So,
Oh,
but you train it from scratch, right? So I'm just curious, how many tokens altogether does it take to push it up to the good, well-rounded, benchmarks?
oh, oh, actually, I would say the more tokens, the better. As you can see here in this figure, if we increase the training budget, the training on more tokens, right, the performance is increasing. And if we are talking about the paper, for example, if we are talking about the apple-to-apple comparison,
Uh-huh,
yeah, we should control the same number of tokens, right?
I see.
Yeah, yeah. So for example, if we are only talking about product or we are only pursuing the best performance, we should train the longer the better. Yeah,
All right.
yeah.
Okay, it's like basically purely hypothetical scenario. Yeah, I'm thinking about something like curriculum learning, because
Uh,
the training of the models is very inefficient. We
yeah.
don't know for what reason. Like maybe is it HD or something else? Presumably we invented, and like the model I have in mind is like child learning, right? First some basic skills, and then eventually one skill at a time. And presumably we came up with a very efficient way of training, like human-like way of training.
Yes.
What do you expect? Like, what's your intuition? How much data would it take to get, like, suppose it's like, would it be comparable to, I mean, it's kind of stupid question, right? Because very fuzzy. Like, would it be like kind of get anywhere near close to the human efficiency if you develop the best possible curriculum? Because that's what you are doing, you're developing curriculum.
Yeah. Yeah, yeah, yeah. I see your point. Yeah, and that's a very great question. Uh, honest, honestly speaking, let me think about it. Honestly speaking, I think current all of the current approaches, including ours, will not be as efficient as human learning, right? Because we need to consume like 1 trillion tokens. Yeah, our human will not read so many tokens, right? We just read hundreds of books, right?
Right, but what I'm talking, it shouldn't be even necessarily a transformer, it could be something else. But
Mm.
suppose we came up with a better architecture, right? A different,
Mm.
not as SGD, whatever, some kind of Bayesian methods. What we are looking for here, like, but we still have the same data to train our fantastic like
Mm.
model.
Mm.
What would happen? Is that,
Yeah,
yeah? Mm-hmm.
yeah, I think curriculum learning is a very good way actually, because currently, as you can see, although I did not use curriculum learning, but it has some embedded philosophy from curriculum learning because there are four phases, right? Phase one is for common sense reasoning, which is more
Right.
basic. and phase 4 is more advanced, like college level mathematical tasks, right?
Mm-hmm.
And yeah, I think if they hope to achieve better efficiency, yeah, we should research on the curriculum learning. Yeah, for example, we should do more fine-grained, like break the competency reasoning into more different disciplines, right?
Okay.
Yeah, I think that would be a helpful way.
Because what I have in mind, well, for example, there was, like baby AGI, some kind of very basic model, right? I
Mm,
forgot, like, was it Meta or was it Benja?
mm,
And some kind of memory transformers, right? So what kind of memories you need to pull from your data if you wanna create a well-rounded models, right? And
mm,
they did experimented. I think Baby AGI, maybe something. I think Memory Mosaics
mm,
experimented with Baby AGI data or something like that.
yeah.
They've been training. Basically, Memory Mosaics. It's they showed. It's very interesting paper. I don't know if you heard from it from Meta. Nobody is interested in it for some reason. But
Uh,
basically, they demonstrated that. Pure like combination of memories is equivalent to transformers with
oh,
attention by like MLP units. Uh,
okay.
and they, I think they experimented, I'm mixing things up. I experimented with Baby I
Mm,
language.
mm,
And right. And also this current approaches, right, when people are trying to train on concepts.
mm,
Basically, what I'm thinking, if suppose you know what concepts are the kind of if you deal not with a big blob of data, but with kind of understand what is it there in data, what you need for reasoning. You need to learn some
yeah,
concepts like when you learn curriculum, some skills,
yeah,
some like if you could split the reasoning and human mind into these components that
yeah.
coming together and give you all this functionality, which we right now kind of moving in this direction, but not quite there yet, right?
Yes, yes, you're right. Yeah, I feel like currently we are using a very stupid way, a very inefficient way actually. As you can see, 1 trillion tokens, right? We need to memorize or mine the patterns behind the trillions of tokens. Yeah, actually for our humans, there are a lot of different abstract reasoning abilities. Like we will, like you mentioned, we will use concepts, right? And
Right,
skills, right? We develop skills, right? Yeah, instead of tokens.
right.
Open level. Yeah. Yeah.
Because how we learn, we don't learn like that. We don't like kind of swallow the huge encyclopedia. Usually we consume knowledge in small chunks, and
Mm,
after we consume the small chunks, we do this work in our mind
yeah.
to connect new concepts to everything that we knew before. That would be a more efficient way to do. No, and build a new models of old models in our mind, and that would be a most efficient way to training. Suppose we have it somehow, then it would be good to know what data we need consume and how much. Yeah, I'm just dreaming. Thank you very much. It's a very interesting direction, very interesting work.
Yeah. Thank you so much for your questions. Thank you.
I think I have also one question regarding to the maybe some downstream task because that when we train the model, we are not actually know all the downstream tasks that we perform on. So how can we ensure that if there's a new task, our data mixing do not lead to a performance drop?
Yes. Yes. That's a good question. So basically, we kind of have well, I will split the answers into two parts. The first one is um let's see, there are domains and tasks, right?
Yeah.
Let's talk about the domains first. If we have a new domain, it would be better if we can have some task data in from it. That would be great. And if we are only talking about tasks inside the domains, we find that this method has a very great transferability, which means we only use 3 tasks, and we could generalize well to many other tasks inside that domain. Considering that the domains could be enumerated, there are only a few domains, right? Yeah.
Yeah.
Yeah. And also we found that we can also generalize cross domains. For example, we are searching the data mixture using like arc, easy, Swag, and Pika. Only these 3 datasets, the validation set. Yeah. And we test our model on a lot of different tasks, including the mathematical tasks. Yeah.
Yeah, and when you do cross domain tasks, when you mix the data, how you define the importance of each domain or you just do just like an average?
Oh, I just transfer. I mean, I will only search once. I mean, search the data mixture on the Pika Swag and Arc-Easy, right? And after identifying the data mixture, I will directly use this data mixture to other domains.
Yeah. I just mean these 3 tasks because they are also have some difference. Yeah,
Yeah.
how do you weight these 3 training tasks?
Oh, no ways actually. They just do mean pooling.
I see. Yeah, that makes sense.
Yeah.
Yeah, because that's one thing that I encountered before is that when I train on some mask data and mix with some pre-trained data from the also the SM small LM, and the problem is that when I test on ArcEasy, Arc challenge that they perform very good, but one day that I try to add the I think the trivial QA and only on this task, the performance drops a lot. Yeah, just I find that on some tasks there should be something that cannot be predicted.
I see. Yeah, I think we also tested trivia QA. Yeah, I think every task performs very well. Yeah, yeah, maybe need to figure out. Yeah, maybe if there is a huge gap between the data distributions, then I think it would be better to include that data distribution in our search process. Yeah.
Yeah, that's and one thing and another thing is that because that we all know that because you mentioned about the reasoning or mask tasks, we all know that for these tasks, the data is already very scarce. Yeah, because there is only very limited data. Just do you think that collecting more high quality data is important for them, or just we can only have this data and doing mixture can improve a lot?
Yeah, if we are only talking about mathematical tasks, I feel like there are a lot of data actually. I mean, for example, NVIDIA recently released Llama Nemotron data, which contains around 15 million data examples. Yeah, I think that's huge. And so I don't think for the mathematical domains the data is sparse. Yeah, but if we are talking about like a new domain where the data is very sparse, yeah, I do think we should collect data first, yeah, or synthesize data first.
Yeah, because let me check. Yeah, because one thing that previously we tried is that we tried to train the small that's 316 billion million versions. Yeah, on the mega mass dataset, if you know that, and it increased a lot about the mass ability from SGS at K that I think that the original maybe just 2 or 3 because they do not use mass specific data and the annealing stage for this small model. But with this new data, that it can improve to maybe 16%. I think it's already very huge improvement for a very small model. Yeah, so I think the quality seems is still very important.
Yeah. And also, I think for advanced reasoning tasks like GSMDK or any mathematical tasks, we need larger model, right? I feel like we need a larger 1 billion model, larger than 1 million model, 1 billion. Yeah, I'm not so sure about like 300 million model. Yeah.
Yeah, thank you very much. I think this is all my questions. Yeah.
Yeah, thank you so much.
Maybe I also have one question.
Yeah, go ahead.
So, you know, I was wondering, like, if we have different architecture, should like we should construct different type of data for enhancing their capacities.
Yeah. Intuitively, just my understanding, I think good data should be general enough. It should be agnostic to architectures. That's only my understanding. And empirically, we had some experiments actually. Very recently, previously we searched the best data mixture on transformer models. I mean, on Nemotron transformer. It is a specific architecture. Basically, it's a not normal transformer. And then we directly transfer the data mixture, which is effective to Nemotron transformer, and we transfer that to other models. For example, we transfer it to Llama model. There are some differences between these two models. And then now we are working on like hybrid models actually. Yeah, although we haven't had some experiment results from hybrid models. Yeah, but from the that transfer from the Nemotron architecture to Llama architecture, we find that the data is good enough. Yeah, we could still see a lot of improvement. Yeah, which is pretty consistent. Yeah, yeah. So
But what about for hybrid architecture?
yeah, for hybrid architecture, we haven't got the results actually.
Oh, still
Yeah,
cool.
yeah, we are still working on that. Yeah, yeah. Actually, Hanba, right? We are using Hanba. Yeah, I can see that we are using the optimal data search from Nemotron transformer, and we are using them into our Hanba project. And although we did not do apple-to-apple comparison, we have had very promising results. Yeah. So we believe the good data, data quality is somewhat agnostic to architectures. Yeah, yes, except you created a very novel architecture which just need like hundreds data or thousands data, which is very advanced. Yeah.
Okay, thank you for your answer. And I was also wondering, like for a hybrid model, like for a recurrent model, do you need to uh, design some tailor designed data to enhance their like their short so ours have like lot of shortcomings and for example like in context retrieval should we construct some data to enhance those capacities for irons?
Yeah. I'm not super familiar with like the advanced architectures, but I would say uh, this method could be generalized to other architectures. And basically, we just because as you can see, the core component is proxy model. Actually, if we switch to a very new architecture, we could just use that architecture as our proxy model. That will ensure a very good performance. Yeah, because if we can ensure the proxy model and the target model are in the same architecture, I think then there will be no issues. The only issue is if we use a different architecture as the proxy model. Yeah, that is not very clear.
Okay, thank you for your answers.
Yeah, thank you so much. I think that's it.
Yeah, thank you for your
Yeah,
time.
cool. Thank you so much. Thank you for your invitation. See you.
See you.